Kinder, perimeter and area with similar polygons. This is chapter 5, lesson 2. I just start with a real simple. Your book makes it more complicated, of course. So if we got the perimeter of this little square, I'm looking at this side length 1, side length 1, side length 1, 1, 1. The perimeter is 1, 2, 3, 4. Add up the sides, right? 4 centimeters. The area is 1 square centimeter. Okay, let's draw a similar figure, right? Another square, but we're going to double the perimeter. So we got a 2 by 2 square. This is side length 1. This is side length 2. So my perimeter of this one is 2 plus 2 plus 2 plus 2, 8. 8 centimeters. So yeah, see, this perimeter doubled, right? And what does the area do? 2 times 2, well, you can see there's 1, 2, 3, 4. 4 square centimeters. 4 square centimeters. So the area didn't just double, the area quadrupled. 4 times as big, the area. Okay, so let's do another one, and maybe we'll do 2 more just for fun. So I'm going to take the first one and multiply by 3. Make it 3 times as long. Each side 3 times as long. So I got a 3 by 3 square. The perimeter is 3 plus 3 plus 3 plus 3, 12 centimeters. So the perimeter is 3 times as big. And what about the area? 3 times 3 is 9 centimeters. So it's 9 square centimeters. You can count them up, 9 little squares. So if we go look back at the original one, if I triple the perimeter, I get, what do I do with this? I increase it. The area has increased by 3 squared. So multiply by 3 here, multiply by 3 squared here. All right? So just thinking about these similar. Okay, we'll just do one more. 4 by 4. And what if I have 4 times the perimeter? The perimeter is 4 times as big. So the perimeter is 16. No, not 16. Whoops. Yeah, it is 4 plus 4 plus 4 plus 4. So the perimeter is 4 times as big. You know, simple, just multiplying. But the area now is 4 times 4, right? There's 16 of these little squares. So when the perimeter of a similar figure, when the perimeter increases 4-fold, the area is 1 times 4 squared. So this is a fundamental fact of geometry, is when you have similar figures and you whatever you multiply the perimeter by, whatever factor, well, you square that factor to get the change in the area between the two. Okay, so let's just jump into the example problems. I'll let you go through your book and look at all their examples and their solutions and whatnot. And we'll just look at these, and these are not as long as, I hope I won't take as long as I have on some of the other ones. Let's see. I can't quite see the top there. Let me move the camera, sorry. All right, chapter 5, lesson 2, activity 1. Scoot that down a little bit. All right, so it just has this triangle here. So your book is not starting out with any proofs of anything, but M is the midpoint of AB, N is the midpoint of AC, P is the midpoint of BC. So it's easy to see that AM equals B, this length, right? These two lengths are equal. These two are equal lengths, right? Because we're the midpoint. That's what midpoint means, divides it in half. These two are equal lengths. And these two down here are equal lengths. Well, because I going from midpoint to midpoint, if you put this on a grid, it would be easier to see. Maybe I should draw it out on a grid, but this side is the same length as these, and this side is the same as those two. And we could mess with the angles here and look at the angles and why the angles are equal. If we drew another parallel line up here and treated this as a transversal, and because this is going to be parallel to the base, right? MN will be parallel to BC, and this side here be. So I'm not going to go through all the proofs and stuff of why it works out like this. I think you can kind of see it and work this one. Maybe make up a. It said the what did it say? Oh, the area of MNP is 50. Well, you can see that these are not just similar, these are congruent. The big triangle is similar. Well, I'll go ahead and sketch that. If you got this, if this line here is parallel to the base, and then I'm cutting this, and you can look at all your angles and how this is a corresponding angle to here, and so these two angles are equal, and then also this line cutting this would be congruent to this. Yeah, this is congruent to this. Okay, you can do out all your angles and make sure that in your mind that okay, you got all these, you got four congruent triangles and then this big one. So this is just like I was showing you. If you start with this, what they've given you here, this 50 centimeters, and you see that this is equal in length to this, well, you've doubled the length for this, right? So this side is double the length of this side. This, now the base is double that. And this side over here is double MP. So this area, you don't double it, right? If I have doubled the perimeter, if I've got the perimeter times 2 in the ABC, well then the area will be times 2 squared. So it's and you can see that it's 50, and there's 4 of those triangles, right? 50 times 2 squared. I don't know how much more of this you really want to know. So that's the answer to that one. Sorry, I didn't say go ahead and do this yourself. You probably already did it in your head real quick. Okay, let's go on and do number 2. So once again, you know you're in this similar chapter, so you're going to have it in similar. Which one is it? Well, you can look at it and make sense of it. And that your book doesn't do a proof of why these are similar figures. You must have done this in another unit. Why BPC is a similar triangle to DPA. Because you're in a circle and the way it cuts out, and this angle is congruent to this angle. And why are these two angles congruent? Boy, that proof, I'd have to go back and look that up. But anyways, you got two congruent triangles. Now, which you can see that the 2 and the 5 should match up in this 4, and this will be a bigger one. We could go ahead and get this side if we wanted to. What would it be? 2 times 5 halves, 20. 4 times 5 halves would be, this would be 10, huh? Is that right? 2 times 5 over 2 would give me 5. 4 times 5 over 2 would give me 10. Yeah, and that makes sense. This side is double that side. This side is double that side. So what about the areas? Well, if let's look at the perimeters first. So the perimeters, the ratio of the perimeters. The perimeter of BCP, triangle BCP, the ratios of the perimeters this one is whatever, DPA, perimeter triangle DPA. Well, the ratio of the perimeters is 2 to 5. Right? The ratio of the small, let's see, were they doing the small one to the big one? Yeah. The small triangle to the big triangle. The ratios of the perimeters is 2 to 5. Well, instead of just doubling, if we were doing it double, if this one was exactly twice as big, then the ratio would be 1/2, right? 1/2, and then the ratio of the areas would be 1/2 squared, would be 1/4. Like this would be 1/4 of this. So these are 2/5. So the ratio of the areas is this ratio, that the area ratio is equal to the perimeter ratio squared. So all it's asking for the ratio. You don't have to find the area. We can't right now find the areas of this. We're not given this angle. We're not given any single angle in here. So we can't find the, work out all the trig and find the exact areas. But we know that the ratio of the areas will be 2/5 squared for 20/5. So, and you can probably tell that what that ratio will be. If I flipped it over, it's almost 24. It's almost 6 times as big. Now, I didn't draw it accurately. And it's probably pretty accurate, right? If this 2 was down here, then I have 2, 4. Yeah, it's pretty close. And you can tell that the area, how many times can I fit this one inside of here? Well, probably close to 6 times, right? So the perimeters ratio is 2/5, and therefore the area ratio is square that. Okay, that's all there is to it.